Let's compare growth functions. In our part A, we did that element uniqueness. We find a solution. Element uniqueness problem. We have method 1, method 2. Let's find the growth function for method 1 and the growth function for method 2, and we do comparison of these two growth functions. Then we can make our conclusion which method is better. Method 1 is better or method 2 is better. Yep. That's the reason we need this concept. Okay. Yep. All right, so let's do the work. Compare two growth functions. Which method is better? Method 1, method 2. We need to get the growth function. Method 1, growth function n squared, right? Method 2, we do two steps. Step 1, n log n. Step 2, n minus 1. The dominant term is n log n. The growth function also n log n. Okay? Growth function of the first method, n squared. Growth function of the second method, n log n. So now we only need to compare n squared with n log n. How about that? Okay? Yeah. When we do comparison, the limit way. Yeah. So we just did in the previous slide, the limit way. So let's do the limit. Calculate the limit of the ratio of these two growth functions. For the comparison. Use ratio to compare two growth functions. Right, yeah. The limit n squared over n log n when n goes to infinity. The ratio. Okay? Yeah. Simplify. Find this. Let's do cancellation. N over log n when n goes to infinity. Calculus. Here we need to use the knowledge of calculus. Knowledge. What's the log base? So here you can assume some reasonable log base. Some reasonable log base. What's the reasonable? Log base A, this A should be a number greater than 1. That's our reasonable log base. Okay? Greater than 1. If less than 1, it's negative. If A is less than 1, this log function is a negative value. So our growth function cannot be negative function. The number of basic operation always positive. Always positive. So we don't consider the negative case. So we assume A greater than 1. Okay? So this function is a positive function. We compare the ratio when n goes to infinity. Here, how to do the comparison. Let me check how much time do I have. Yeah, all right, I still have a few minutes. All right, the answer is infinity. Can you see that? The answer infinity, n over log n, answer infinity. So we need some knowledge to see it. We need some knowledge to see it. Here, how to see it? I'll show you some ways to see it. Method 1, variable substitution. Because log, usually we're not familiar with log, right? But log is always, so most people, most of our students feel it's hard to handle log functions. If it's hard to handle log function, can we use a new variable to substitute the old log function? That log is gone. After that substitution, the whole log function is gone. So we do not need to deal with log. Okay? So that's one way to avoid it. That little u equals that log base A of n. We introduce a new variable, little u, to get around log function. Okay? After we introduce this function, then we can represent n as exponential function with a base, a to the u exponential function. Okay? Yeah. All right, so n equals, let's go back to the ratio. After variable substitution, we will have numerator a to the u over denominator just the u. And u also goes to infinity. Because when your n goes to infinity, u also goes to infinity. Okay? Yeah. This time, you do not have log function. Okay? You don't have the log function. Yeah. But what do you have? You have exponential function in the numerator and just a linear function at the denominator. Now, can you see when u goes to infinity, this ratio goes to infinity? Can you see that? Because we know exponential function dominates any polynomial, right? Do you know? Exponential function always dominates any polynomial. This is a special polynomial. Okay? Special polynomial. This is exponential function. Exponential function and exponential function dominates any polynomial. Yeah. That's our, real life experience. Yeah. But we can prove it. If you still you do not feel comfortable to accept this fact, okay, we can prove it. Yeah. In our next class, I will show rigorously, we use rigorous math to prove it. Yeah, we will do that. Next class. Okay, part C and part D. We will do the proof. Yeah. Question? Yeah.
Is then that like the math that proves this very important to know, or is it just like a good concept to see written out?
The method is important.
Math.
Yeah, the math, because the math not just prove this special example, we need to use to work on many other examples. Yeah, but for this class, I may not require that much math. Okay? Yeah, I show you how to do. Yeah, but you just know it. Yeah. In my questions, I may not give you such problems, such questions. But good to know
Yeah.
those things, techniques.
I like showing things.
Yeah. But for the questions, we mainly focus on computer science questions. Not a little small portion of math questions, yeah, but should not be too much. All right, so let me come look at the time. Time thing 42. Yeah, so but let me Nobita's rule. That's our calculus 2 content. Okay, yeah. Here I just show you how to use this powerful tool to compare two growth functions. One grows faster than the other. Yeah. All right. All right, so the method 2, yeah, because we compare method 2 with method 1, yeah. When we use the L'Hopital's rule, the basic the method is this. Yeah. We need to find the limit of ratio of two functions, two original functions. But usually that ratio sometimes hard to find directly. The limit hard to find directly. But based on the L'Hopital's rule, we can take the derivatives of those two functions. Yeah? So you do not compare two original functions, you compare their derivatives. And we hope when we work on the derivatives, we can find the limit easier. Yeah. So that's the main step we need to use here. Yeah. Derivatives. Yeah. Okay. Yeah. So that's a simple idea. But before you apply it, you need to check if it's legal to apply the L'Hopital's rule. You need to check the condition. It may not be legal. You may apply in the wrong way. Now, so what's the right way? You need to make sure you apply on indeterminate form. Indeterminate form. Infinity over infinity. Yeah? Two functions, both functions go to infinity. That's we call infinity over infinity form. Okay, it's the indeterminate. Yeah, because it could be anything. That ratio could be anything. It's not determined. Not determinate. Okay, could be anything. Okay. Could be zero, could be constant, could be infinity, could be anything. That form. Okay. Yeah, so we call it indeterminate form. Another possible indeterminate 0 over 0. But here, because we use it in our algorithms, we do not have static indeterminate. In math, you may have a second indeterminate form. But in our algorithms, we only have the first indeterminate. Because our growth functions usually go to infinity. All right. Yeah. Yeah, but in math, actually, there are a few more indeterminate forms. Yeah, but here for example, 1 to the infinity. That's another indeterminate form. Yeah, yeah. Infinity to the zeros, right? Indeterminate. Okay. In math, there are many different indeterminate forms, but for our algorithm, the only one you need is this one. And also, yeah, for example, times 0. Okay, could be anything. Indeterminate could be anything. Okay, yeah. All right. Now, so let's look at first. We know this is indeterminate form, a to the u. The numerator function goes to infinity, and denominator function also goes to infinity. So no problem. It is an indeterminate form. So we can apply L'Hopital's rule here. Okay, yeah. Then we take the derivatives. The numerator, denominator, derivative of u, 1. That's easy. Derivative of u is 1. Yeah, I hope you can still remember the simple one. But exponential function a little harder, so we can find its formula somewhere. Okay, yeah. On web or in your textbook, yeah, old textbook, yeah. That is natural log of a times a to the u. Yeah. That function, yeah. Natural log of a. Okay, yeah. All right. So now after you take the derivatives, then you can get the answer easily, right? Denominator just 1, very simple. Yeah. But the numerator in the parentheses, it's a constant. Natural log of a, it's a constant. A to the u, that function should go to infinity. That function, when u goes to infinity, that function also goes to infinity. So the answer is infinity. Infinity over 1, so that's also infinity. Yeah. So you can see we get, this is rigorous proof. Yeah. When u goes to infinity, a to the u over u goes to infinity. Rigorous proof. Yeah. Okay, yeah. All right. Yeah, so this is one simple example. We use L'Hopital's rule to compare two growth functions. All right. Yeah, but here, yeah, we need to make sure our A is greater than 1. Then natural log of A is positive. Yeah. Natural log of A is a positive number. Yeah. All right. Yeah. Yeah, but there is another issue here. Yeah. So I try to make sure all our logical reasoning rigorous here, because you take derivatives of 2 growth functions. How do you know you can take derivatives of 2 growth functions? Last step, you need to make sure it's legal, right? So then the next step, I try to address this question. When you take derivatives, you need to make sure that step is legal. Okay, yeah, here. Why you say sometimes legal, sometimes illegal? Because you need to make sure the functions that you take derivatives must have continuous variables. Continuous variables. The variable change continuously. Okay? Not taking random value, not taking discrete values. Discrete value. Okay? Yeah. So here, let me show you another example. So what's the difference between discrete variables and continuous variables? Look at this ratio of 2 functions. N over log n. We know n can only take discrete values, right? 1, 2, 3, 4, discrete values. N is not a continuous variable. N is not continuous variable. Okay? So it's a discrete variable. Discrete variable, a function using discrete variable, you cannot take derivative. It's illegal. It's illegal. Okay? So we need to make this step rigorous. Yeah? We need to make this step rigorous. Okay? Unfortunately, in our textbook, this step is not rigorous. It just takes derivative on random variable, on discrete variables. Okay, not rigorous. Yeah. So, all right. So let me show you how to make it rigorous. The question.
Maybe it's obvious for people, but how come in the previous iteration when we were looking at AU over U wasn't considered continuous or is considered?
Yeah, good question. Actually, yeah. So here, the question, yeah. So actually, if we go back, connect to the original functions, and not continuous. Okay, not continuous. Also discrete. Yeah. But we can, there is an option we can think of. We can do this problem on continuous variable. Then we go back, right? So that here, the way we do, I show you here. After I show you the way here, then you use the same way, going back. Yeah. Actually, that's a very good question. Yeah. Actually, here we bypass that rigorous step. We bypass. Okay. Yeah. But here we bring it back. Yeah. So we skip that step. Now we bring it back. Yeah. All right. We know discrete variables. Now, can we write their continuous counterparts? Yeah, the function, but we use continuous variable. They're corresponding continuous functions. Okay, yeah. So we consider, how about we consider this new limit? This time we assume x continuous variable. Yeah. So here you can see they have the same form, but the values, one discrete values, another continuous matrix.
Wait, how come?
So here, we consider, hold on. Our goal, we need to find that, okay? Here, we change our problem slightly. We do not say they are the same, okay? But we change the problem slightly. Can we modify the problem to this one? Calculate this figure. All of that. We just calculate this figure. But when we calculate the limit, our x goes to infinity, x changes continuous. So it's a continuous function. Here we're not allowed to make any change continuous, only discrete values. So that's the difference. Here we are allowed continuous, change continuous, right? You can treat as two different questions, but they're closely related. All right, but good thing is you can take derivatives. Because we use continuous variables, we are allowed to take derivatives. Derivatives are well defined. For discrete derivative is undefined. You cannot define derivatives. Undefined.
So if we were like given this in a homework problem and we ended up with the equation on the left and it said, okay, instead, let's consider this, so we can
Yes.
solve this.
Yes. Okay. Solve this, then you can answer, go back. Go back. Okay? Yeah. All right. Yeah. But I will explain why we can go back. Okay? Another tricky step. Yeah. Hard to understand. All right. Now we consider this closely related question. We know it's different from the original one. Yeah. So this time we are allowed to use the L'Hopital's rule. Okay? Limit numerator, it's 1. Okay? Limit of numerator is 1. Let me review a little bit. Yeah, if you ask me why 1, the numerator we can consider we have a power function. Power function, x to the n, that's a power function. Okay? For the power function, it's derivative. Yeah, this prime means derivative. Okay, the prime derivative. The formula is n times x to the n minus 1. Okay, this is the derivative formula for the power function. Any n. Okay, yeah, any n. Yeah. All right. Here, n equals 1, x equals 1 times x to the 0, so that's 1. Yeah. Power function, derivative. All right. Denominator, log base a, assume log base a, 1 over natural log, bracket, natural log times x. That's the formula, derivative of log formula. Okay? Yeah. After simplification, okay, yeah, reciprocal, yeah. Natural log of a constant times variable x, but x goes to infinity. This is a positive constant, yeah, because this natural log of a with a greater than 1, it's a positive constant number. Okay, yeah. So the limit is infinity. This, by applying L'Hopital's rule, we found this limit, x version, this limit is infinity. Okay, all right. Then we go back to original question. We find the limit is infinity. We go back to our original question. We say that limit equals infinity. That limit equals infinity. Why? Yeah. Let me explain why. Why we can go back? Okay? Why we can go back? Okay? It's legal. It's rigorous. The reason is by the definition of limit. By the definition of limit. So here we need to recall the definition of limit. Here, this limit, all right? This limit. Now you agree, the first thing you agree, this limit equals infinity. No problem, right? By L'Hopital's rule, it's rigorous. Okay? So this limit equals 0. When x approaches to infinity, this limit equals infinity. The question is, what do you mean x approaches infinity? X approaches infinity. What I mean, my question here is, in what way x approaches infinity? Approaching infinity, there is many different ways, right? Yeah. So here my question is, here, let me draw number axis. This is number axis. This number axis goes to infinity, right? Yeah. But our x approaches infinity, we take a sequence of x values approaches to infinity, going along that infinity direction, goes to infinity. Do we have any restriction on x? What kind of values we can take to go to infinity? How to go to infinity? Do we have that information? No, right? No restriction. That means you can take arbitrary way. Okay? It's correct. When x goes to infinity, in arbitrary way, goes to infinity, always correct. Okay? Yeah, x goes to infinity. So you can take, let's select x values goes to infinity. Okay? X 1 square, 2 square, can we take it this way? 3 square, n square goes to infinity. Let's go to infinity, right? Yeah. Can we take 1, 3, 5, all the numbers go to infinity, 2n minus 1 to infinity, right? Can we take even numbers to infinity, 2, 4, 6, 2n to infinity? All legal, right? Then, how about we take a special discrete values, go to infinity? That's 1, 2, 3, to n. When we take this sequence, is it we recover to the original question? Goes to infinity, right? We just take special x values. Yeah. So we do not apply L'Hopital's rule on the original ratio of growth functions. We apply here, it's legal. After we get the result, we interpret it. Yeah. Because by the definition of limit, we can take x values in any way that approaches to infinity, all legal. How about we just take the special x values, discrete values, okay? Yeah. If we take special x values, that's exactly our original limit form. Yeah. So we get around it. It's legal. Yeah. And we didn't apply L'Hopital's rule to discrete variable functions. We didn't do it. We didn't apply directly. And we apply in their continuous counterparts. No problem, right? Yeah, no problem. Rigorous. Yeah. Yeah. All right. Try to understand. Yeah. Yeah. With that, now we have no problem. Later, yeah, as you said, when you have discrete ratio function ratio, you write this version, apply L'Hopital's rule, get an answer, then you come back. That's perfect. Yeah. That's perfect. Yeah.
So the limit of a natural log of a, that one goes to infinity, right?
Limit. Next. Yeah. This is constant. Constant time, this is infinity. Yeah. This a never changes.
Okay.
Positive, A greater than 1, so this is greater than 0, but we fix it. Then we change this number.
Okay, that makes sense.
Yeah.
Okay. The A was throwing one.
Yeah. Even this number very small, doesn't matter, 0.0001, but this X could be very large.
Okay, gotcha.
All right, so we complete our part B. Yeah. All right, so the conclusion, yeah, so hope you can see it, or I just erase it. All right, conclusion. Yeah, after we do the comparison, the conclusion, algorithm with growth function n log n, yeah, that's our second method. Method number 2 is faster than the one with growth function n squared, the first method. Okay. So that means we should take method number 2 for this question. Yeah. And here you can see for this algorithm, we do sorting is better than we do not do sorting. Yeah. Question? Yeah.
Where did we get the n squared from? Was that on a previous slide?
All right, previous, remember we tried to, several steps, ignore some constant, we get n squared. Remember in the previous slide? Yeah. Oh, no. Yeah, because previous, so here, let me just, I need to quickly, yeah, I just moved to previous slide, all right? Yeah, this slide. Okay. All right, look at that. How do we simplify our efficiency function? Let me call efficiency function.
Yeah.
To this one. All right, first, we only keep the dominant term. Yeah. -1 minor term, we ignore it. First step. Second step, we ignore the constant. So we get a growth function n squared. Yeah. Try to make it as simple as possible by ignoring some less important constant terms. Similarly, this one, because the first term dominates all the other terms.
And we just proved now that why they do, or how they do.
Yeah, now we prove we compare these two growth functions.
Makes sense.
Growth functions. All right, yeah, so that's part B.